Let's begin. We are now going to be on to the flyweight pattern. So what I've been doing for this is just a pretty simple standard. I'm reading through this. This is also for me myself, but I do know like there's some people like me who are dyslexic who may this may be helpful to like listen to somebody hear somebody talking, reading it while they're reading it. Might be helpful. Maybe you can go through it like 2 times speed or whatever. I'm not a professional reader, so I sometimes diverge into my own thoughts on it, but yeah. All right, with that, flyweight pattern. The fog lifts, revealing a majestic old-growth forest. Ancient hemlocks, countless in number. Ooh, I need to do that. Where was I? Ancient hemlocks, countless in number, tower over you, forming a cathedral of greenery. The stained glass canopy of leaves fragments in the sunlight golden shafts of mist. Between giant trunks, you can make out the massive forest receding into the distance. This is the kind of otherworldly setting we dream of as game developers, and scenes like these are often enabled by a pattern whose name couldn't possibly be more modest: the humble flyweight. Zerkines, good morning. The last link doesn't work for you. The gameprogrammingpatterns.com to this website. It should, if I hit refresh. Yeah, it's still up there. Let me make sure. Dato, good morning. Finally an ASMR stream. Yeah, I guess I could also do sound effects and voices. I'll do voices when we have different characters. Luckily, there's no characters, so it's easy for me. Forest for the trees. I can describe a sprawling woodland with just a few sentences, but actually implementing it in a real-time game is another story. When you've got an entire forest of individual trees filling the screen, all that a graphics programmer sees is the millions of polygons they'll have to somehow shovel onto the GPU every 60th of a second. We're talking thousands of trees, each with detailed geometry containing thousands of polygons. Even if you have enough memory to describe that forest in order to render it, that data has to make its way over the bus from the CPU to the GPU. Each tree has a bunch of bits associated with it, a mesh of polygons that define the shape of the trunk, branches, and greenery, textures for the bark and leaves, its location and orientation in the forest, tuning parameters like size and tint so that each tree looks different. If you were to sketch it out in code, you'd have something like this. Let me make that a little bit bigger. If I do that, and then put myself over to the side like that. This does kind of look a lot like what we've been creating. So we have a class tree. By the way, all these examples are in C++, but they're trying not to use anything special in C++. So then they have a private object. So then we have our mesh. We have our, so like then they have the textures. We haven't done textures with any of our stuff. We just have the mesh. Then position, height, then like the thickness of well, I guess the tree, and then tints. So then colors. So that ours are even like more complicated, and we have less stuff going on, which is that's cool. That's a lot of data and the mesh and textures are particularly large. An entire forest of these objects is too much to throw at the GPU in one frame. Fortunately, there's a time-honored trick to handling this. The key observation is that even though there may be thousands of trees in a forest, they mostly look similar. They will likely all use the same mesh and textures. That means most of the fields in these objects are the same between all of those instances. So yeah, we have a bunch of trees. Each of them has a mesh, each of them has bark, each of them has leaves, and each of them have their own parameter, like position parameters. We can model that explicitly by splitting the object in half. First, we pull out the data that all trees have in common and move it into a separate class. Okay, so class tree model, private, mesh, texture bark, texture leaves. Okay, so we're going to take all of these similar stuff out. Now, I noticed that the location stays the same, but I guess that's because the value is if the values are the same, not just the type is the same. The game only needs a single one of these, since there's no reason to have the same meshes and textures in memory 1,000 times. Then, each instance of a tree in the world has a reference to that shared tree model. What remains in tree is the state that is instance specific. Okay, yeah, that's very true. I think for like the player and some of the other things I've done in the past, I put the shared things into the global game state. But it sounds like this should be its own separate struct, essentially, in Rust to hold those shared things, but for each individual thing. So in tree, for example. So that means we have class tree. Interesting. So they're going to store a reference. I believe that the asterisk here is a reference. They're going to store a reference to a instance of a tree model. I wonder if tree model is going to be a singleton then. Vector, so okay, then it's going to store its position, its height, its thickness, and then its individual color to make it look different. You can visualize it like this. Okay, so we have the params in a position here, and then they all point to a single model, which is the mesh, bark, and leaves. This is all well and good for storing stuff in main memory, but that doesn't help rendering. Before the forest gets on screen, it has to work its way over to the GPU. We need to express this resource sharing in a way that the graphics card understands. 1,000 instances. To minimize the amount of data we have to push to the GPU, we want to be able to send the shared data, the tree model, just once. Then, separately, we push over every tree instance's unique data, its position, color, and scale. Finally, we tell the GPU, use that one model to render each of these instances. Fortunately, today's graphics APIs and cards support exactly that. The details are fiddly and out of scope for this book, but both Direct3D and OpenGL can do something called instanced rendering. He has a link to the Wikipedia article for geometry instancing. In both APIs, you provide two streams of data. The first is the blob of common data that will be rendered multiple times, the mesh and textures in our arboreal example. The second is the list of instances and their parameters that will be used to vary that first chunk of data each time it's drawn. With a single draw call, an entire forest grows. Which, yeah, that makes a lot of sense. And of course, if we wanted size to sort of like, or maybe age or something, to like have the tree be small and then grow over time, We still have the same meshes, we still have the same everything else, but now we can just say, okay, you are scaled differently. The flyweight pattern. Now that we've got one concrete example under our belts, I can walk you through the general pattern. Flyweight, like its name implies, comes into play when you have objects that need to be more lightweight, generally because you have too many of them. With instance rendering, it's not so much that they take up too much memory, as it is that they take too much time to push each separate tree over the bus to the GPU, but the basic idea is the same. The pattern solves that by separating out an object's data into two kinds. The first kind of data is the stuff that's not specific to a single instance of that object and can be shared across all of them. The Gang of Four calls this the intrinsic state, but I like to think of it as the context-free stuff. In the example here, this is the geometry and textures for the tree. The rest of the data is the extrinsic state, the stuff that is unique to that instance. In this case, that is each tree's position, scale, and color. Just like in the chunk of sample code up there, this pattern saves memory by sharing one copy of the intrinsic state across every place where an object appears. From what we've seen so far, this seems like basic resource sharing, hardly worth being called a pattern. That's partially because in this example here, we could come up with a clear separate identity for the shared state, the tree model. I find this pattern to be less obvious, and thus more clever, when used in cases where there isn't a really well-defined identity for the shared object. In those cases, it feels more like an object is magically in multiple places at the same time. Oh, okay. I mispronounced. I didn't have the enunciation in the right place. Let me show you another example. A place to put down roots. The ground these trees are growing on needs to be represented in our game too. There can be patches of grass, dirt, hills, lakes, rivers, and whatever other terrain you can dream up. We'll make the ground tile-based. The surface of the world is a huge grid of tiny tiles. Each tile is covered in one kind of terrain. Each terrain type has a number of properties that affect gameplay. A movement cost that determines how quickly players can move through it, a flag for whether it's a watery terrain that can be crossed by boats, a texture used to render it. Because we game programmers are paranoid about efficiency, there's no way we'd store all of that state in each tile in the world. Instead, a common approach is to use an enum for terrain types. After all, we already learned our lesson with those trees. Yeah, I haven't made a 4X or a Civilization or any kind of tile turn-based moving game. But I guess it's always felt really overwhelming to me at the same time. So this type of thing is, I think, the kinds of patterns that would help a lot with that. Okay, so they're showing an enum terrain. Okay, so terrain grass, terrain hill, terrain river. So basically, we're just storing what type it's going to be. Then the world maintains a huge grid of those. So class world, we're going to have, so terrain tiles, looks like it's going to be a vector of vectors. So that means, or array if you're coming from JavaScript. So tiles will then have a width as its first array and height as the second. Am I reading that correctly? I think I'm reading that correctly. Oh, I see. So it's the entire world. So it's a grid pattern. So it's a pretty standard grid pattern where the first tile in the up left corner, so up here, that's going to be 0, 0. So it's not the width of the tiles. This is the width of the entire like world, like how many tiles potentially. So if we have 50 across, 49, position 49 will be the final one over here. To actually get the useful data about a tile, we do something like initialize the world, get movement cost. Okay, so on world, we run the static method, get movement cost. We pass it in X and Y for the specific tile. So now we can go tiles X and Y. So they do a switch statement. We could do a match in Rust. Tiles X and Y. Then we have our different cases. So we figure out which enum variant is it, and then we return what it is. What I think is interesting in Rust is that we can store these specific numbers inside of the enum as well, which might make it a little bit easier. Then we're gonna have, okay, so a Boolean world is water. Okay, so then we ask, hey world, is this terrain water? And then it returns true or false, depending upon what type it is. Oh, so that's interesting. So that's basically mapping these out. So we can't necessarily store that in there unless I have extra logic built in. Let's see, as a sidebar, here I'm using a nested array to store the 2D grid. That's efficient in C, C++, because it will pack all the elements together. In Java or other memory managed languages, doing that will actually give you an array of rows where each element is a reference to the array of columns, which may not be as memory friendly as you'd like. In either case, real code would be better served by hiding this implementation detail behind a nice 2D grid data structure. I'm doing this here just to keep it simple. So like I guess a hash map might work out, or an object where I can have the X and Y together be the key, and then the value is the actual tile. You get the idea. This works, but I find it ugly. I think of movement cost and wetness as data about a terrain, but here that's embedded in code. Worst, the data for a single terrain type is smeared across a bunch of methods. It would be really nice to keep all of that encapsulated together. After all, that's what objects are designed for. It would be great if we could have an actual terrain class. Like, okay, so now we have a terrain class. Here we have the terrain constructor, so it's going to take a movement cost, the Boolean if it's water, and then the texture that I guess it's going to be rendered with. And so then it's going to store the movement cost is water and texture internally. Oh, interesting. So, oh no, that's okay. Private. So here's the private variables that they're then referencing or storing in here. I'm not really familiar with the parentheses that are being used for this. That sort of looks like it's calling a method, which like the methods are being returned here. So int get movement cost, return movement cost, which I'm guessing is being stored here. I think that's how it's working. But all right, basically we have a terrain, we initialize it with what type of terrain it is, the data it needs, and then there's functions to get the various pieces of it. You'll notice that all the methods here are const. That's no coincidence. Since the same object is used in multiple contexts, if you were to modify it, the changes would appear in multiple places simultaneously. That's probably not what you want. Sharing objects to save memory should be an optimization that doesn't affect the visible behavior of the app. Because of this, Flyweight objects are almost always immutable. Oh, interesting. So we need them to be immutable. Well, Rust would help with that very easily. Doing this in JavaScript might be a little bit more difficult because of that immutability thing. But we don't want to pay the cost of having an instance of that for each tile in the world. If you look at that class, you'll notice that there's actually nothing in there that's specific to where the tile is. In Flyweight terms, all of a terrain state is intrinsic or context free. Given that, there's no reason to have more than one of each terrain type. Every grass tile on the ground is identical to every other one. Instead of having the world be a grid of enums or terrain objects, it will be a grid of pointers to terrain objects. Okay, so we have our class world. We're back to the class world. We're back to terrain tiles with a grid of X, Y. Each tile that uses the same terrain will point to the same terrain instance. So we're not going to create one of these terrain instances for every tile. We're going to create one for every type of tile. So as they have here, we have a grass terrain, we have a river terrain, and a hill terrain. So we only need 3 as opposed to however, like if it's civilization, the extra large map, that'd be hundreds, if not thousands of tiles. Since the terrain instances are used in multiple places, their lifetimes would be a little more complex to manage if you were to dynamically allocate them. Instead, we'll just store them directly in the world. Okay, so the global world. So we need that world state. So it's not in like the global main top state. We create a world state and put them in there. So grass terrain, hill terrain, river terrain, they just go in there. We initialize them, and then they're stored for later use. Then we can use those to paint the ground like this. Okay, so in world, we have generate terrain. So the world is also apparently going to be in charge of drawing out everything. So fill the ground with grass, 4 and X. Okay, so we're going to loop through all the terrains. I guess we're not going to loop through all the terrains. We're going to loop through, where is it? All the tiles. So loop through all the tiles. Determine if it's a hill or, okay, yeah, so it's gonna be hill or of a grass. And then basically just plonk it down. And then lay a river. Okay, so this looks like it's gonna be like a one-time create that. This actually might be interesting to sort of like implement across a huge number of X tiles. Maybe that's something we can do after the infinite runner. Sidebar, I'll admit this isn't the world's greatest procedural terrain generation algorithm. Right, because the rivers probably won't actually hook up with each other. Now instead of methods on world for accessing the terrain properties, we can expose the terrain object directly. Okay, so we have terrain, a reference to terrain. Okay, so we're going to run get tile and then pass it in the X and Y, and then we return that specific tile. Although, yeah, I guess that is, yeah, it's going to return the terrain for that object, even though it's just a reference. That's why. This way, world is no longer coupled to all sorts of details of terrains. If you want some property of the tile, you can get it right from that object. Okay, so if we want world get tile 2, 3, and then dot movement cost. The movement cost, if you remember, was on the terrain object. So if it's like a planes, movement cost would always just return 2. But the world doesn't need to worry about that. The terrain itself does. We're back to the pleasant API of working with real objects, and we did this with almost no overhead. A pointer is often no larger than an enum. What about performance? I say almost here because the performance bean counters will rightfully want to know how this compares to using an enum. Referencing the terrain by pointer implies an indirect lookup. To get to some terrain data, like the movement cost, you first have to follow the pointer in the grid to find the terrain object, and then find the movement cost there. Chasing a pointer like this can cause a cache miss, which can slow things down. For lots more on pointer chasing and cache misses, see the chapter on data locality. So we'll get into that in a future chapter. As always, the golden rule of optimization is profile first. Modern computer hardware is too complex for performance to be a game of pure reason anymore. In my tests for this chapter, there was no penalty for using a flyweight over an enum. Flyweights were actually noticeably faster, but that's entirely dependent on how other stuff is laid out in memory. What I am confident of is that using flyweight objects shouldn't be dismissed out of hand. They give you the advantages of an object-oriented style without the expense of tons of objects. If you find yourself creating an enum and doing lots of switches on it, creating this pattern instead, consider this pattern instead. If you're worried about performance, at least profile first before changing your code to a less maintainable style. And then see also, in the tile example, we just eagerly created an instance for each terrain type and stored it in the world. That made it easy to find and reuse the shared instances. In many cases, though, you won't want to create all of the flyweights up front. If you can't predict which ones you'll actually need, it's better to create them on demand. To get the advantage of sharing, when you request one, you first see if you've already created an identical one. If so, you just return that instance. This usually means that you have to encapsulate construction behind some interface that can first look for an existing object. Hiding a constructor like this is an example of the factory method pattern. In order to return a previously created flyweight, you'll have to keep track of the pool of ones that you've already instantiated. As the name implies, that means that an object pool might be a helpful place to store them. When you're using the state pattern, you often have state objects that don't have any fields specific to the machine that the state is being used in. The state's identity and methods are enough to be useful. In that case, you can apply this pattern and reuse the same state instance in multiple state machines at the same time without any problems.